Good evening, everyone. My name is Carlos Olivas, and this is the Extranet project presentation for MEC 1321 Statics class. I divided this presentation into four main key points, which you will see here. So now that you have some insights onto why we are doing this kind of experiment, let's dive into the project itself. And first, what's a Mars lander, and why are we um, dedicating an entire project to these structures? Well, these landers are spacecrafts created with the purpose of landing on Mars and exploring the planet itself. But it's not as easy as it sounds. They need to have this specific design so that they can hold a landing at incredible speeds and um, atmospheres. So this project's objective is for us students to design and conduct one of these Mars landers with any type of commercial pasta, whether it is spaghetti, macaroni, or whatever else you have planned for. Um, the design of the lander will be based of concepts learned in this statics class, as well as new concepts from mechanics, which we students must research on our own and be more familiar with these mechanics concepts since we are being prepared to take this class next semester. Here you can see the design requirements, which is a minimum drop height of 1 meter, maximum weight of 450 grams, a maximum landing pad size of 30 centimeters by 30 centimeters, and glue can only be placed at the joints of the lander, not along the members. Also, the materials used for this experiment will be any type of commercial pasta, hot glue, and a plastic bag or strings, optional in case we wanted to make a parachute. So now that we have the basics out of the way, let's dive into the brainstorming part of the experiment, which will consist on some research I did about Mars landers as well as some prototype designs I created for my own Mars lander. First, let's talk about the InSight lander, which has been one of the most successful recent landings on Mars. And let's talk a bit about its landing structure, which you can see here to your right. We can see that its structure for landing is composed of mainly truss systems. Um, all of the joints are positioned in a way that it creates such triangles that have the force and the power to withstand such an incredible amount of weight, as you can see here in the picture. And this Mars lander was designed to give the planet of Mars its first thorough checkup since it was formed 4 billion years ago. Um, and I was saying this is one of the most recent Mars landers that have been successful since this lander was launched May 5th, 2018 and landed on the planet on November 26th, 2018, which is amazing to see such an recent date for such an incredible project. And currently, this lander is stationary in Mars, continuing its mission. But now let's talk about a much older Mars lander. But as you can see, the structure of the lander itself, it's pretty much the same. You can see the same like truss systems on the bottom, which are pretty much identical to the InSight lander. However, this lander is back from 2007, 2008. Um, but as I saw these designs and these structures, it gave me the idea of creating something similar for my own Mars lander, a landing zone which will consist of triangle truss systems, which would support um, the majority of the load consisting of the egg. And now let's dive into the next slide. So let's now talk about the preliminary designs. some of the advantages and disadvantages for each of them, as well as why I chose the design I chose. So to your left, you can see the letter A design, which consists of a triangular base and some truss systems right on the bottom, as you can see. However, I had the idea of filling the insides of these truss systems with some macaroni so that it would harden the surface, and once it impacted on the land, all of the force would impact into these um, macaroni at the bottom. However, uh, one disadvantage that I saw about this is that the weight increased exponentially, meaning that it was heavier than I wanted, and this could create some sort of damage to the egg itself. So that's why I chose the letter B design that you can see to your right, which consists of a rectangular base, which has four truss systems. Well, one truss system on each side, for a total of four trusses, and three thick pasta rolls, which would be glued to the bottom in order to act as the second structure of impact once the lander was hitting the floor. So now that you saw my preliminary designs, let's talk a bit about why I chose the final designs in these next slides, as well as the conclusions of the project. I ultimately decided to go for design letter B, as you can see here, mainly because the fact that the other lander was so much heavier um, would result in a harder impact to the floor, which could ultimately hurt the extra. So that's why I decided to choose letter B design, and also because this design has a rectangular structure which allowed me to distribute more load into the several trusses I designed, as well as the thick pasta on the bottom acted as the second surface of impact, allowing the egg to be much more safe. And as you can see to your photos to your right, I decided to boil some spaghetti and use this as a cushion for the egg. We can now dive into the equations required for this project, and first let's talk about velocity and normal force. So to calculate the velocity of any object in freefall, we use this formula you see here to your left, which is velocity squared is equal to initial velocity squared plus 2 times the acceleration of gravity and the value of distance of the fall. A represents the value for acceleration of gravity. B0 squared represents the value of initial velocity, which in this case is equal to 0, and x is the value for the distance of the fall, which in this case is 1 meter. Once we have replaced all these values into our formula, we ended up with a value of 4.43 meters per second being the velocity of our lander when dropping freefall. Now let's talk about a bit about normal force, which was equal to 0. But as you can see, this means that when an object is falling at 90 degrees on the vertical plane, then the normal force will always be 0. And since we are talking about freefall, then the normal force will always be equal to 0. To your left, you can see the final design used for the lander with the specific dimensions for each of the sides. However, for this structural analysis, we will use one of the legs of the lander to report the forces transmitted through this set leg. So here we can see a free body diagram of one of the lander's leg with its specific measurements as well as the angles that consisted for each of the joints of the triangle. To the middle of these presentations, you can see all the work I did in order to get all the forces acting on the AC plane as well as the AB plane, and lastly the BC plane. You can take some time um, seeing some of my work, but the main thing you need to know is that I used the weight of my lander, which was 162 grams, and converted these into newtons, which was equal to 1.56 newtons. And once I had this value, I was able to come out with all the values you see here now, which the force for the AC is equal to 1.59 newtons, the force for AB is equal to 1.89 newtons, and the force for BC is equal to 1.89 newtons as well. As I previously mentioned, the weight of the lander was 162 grams, and this was necessary in order to determine the performance of my Mars lander. And the formula I utilized for this performance was drop height over the weight of the lander, which was equal to 1 meter over 162 grams, which gave me 0.00617 meters per gram. Lastly, I will show you a video of the final design as well as a simulation I created in a truss software system as well as my conclusions for the experiment.
My first design
But
for
here
the
I'll
extra
first show you
problem.
the video of the final design.
This is gonna be the 1 meter fall. Let's see if it survives. Okay, so as you can see, some of the well, basically all of the base of the rocket of the lander has been destroyed. However, the egg is intact. And well, here as you can see, the egg is fully intact. Just the lander received all the damage. Yeah. The egg is fully intact. Just the lander received all the damage. Yeah.
Here you can see a simulation of the lander created on a truss system software. So, in conclusion, the objective of creating a lander that would protect an egg from a 1 meter fall was achieved. While the lander's base was destroyed at the impact, the egg survived perfectly. I I believe I learned a lot of concepts such as velocity, truss system, and structural analysis way better with this project, and it's been really fun being able to be creative in designing this kind of landers. If I was able to redesign my lander, the main changes that would occur at the legs of the lander, I would create a few more trusses at the bottom, which would have been easily added to the design, and this would allow for a unstabler landing zone. However, this would be all for my project. I hope you understood most of what I said. I hope you have a great day and thank you for listening.